Wow, what's this? Are we plotting complex numbers now? I think if you remember back to the last presentation, I had this diagram there for you, this one here. And yes, look, we're going to make the x-axis the real axis and the y-axis the imaginary axis, and actually plot the complex number 2 plus 3i like that. And this is like vectors, isn't it? Thinking about displacing, if you like, the origin out to the point 2, 3, which if we relabel the axes will be 2 plus 3i. I guess you can see what's coming up. There's a big overlap here between this area and both coordinate geometry and vector geometry. Okay, and that's what's going to happen in the next couple of presentations. We're going to pursue this. What else can we do? Look at this question down here. What else can we do with them? Well, it's going to get very exciting. You're going to be amazed at how this is going to actually just blow up, and we're going to have a lot of excitement with the things we can do with complex numbers. So here's our basic idea now, driving this presentation, is that the vector OP, represented by xy, if we've done some vectors before, represents the complex number x plus yi. We are actually moving the origin, if you like, displacing from the origin, x in the real axis and y in the imaginary axis. Not a bad idea, is it? Because we've done a fair bit of work on the Cartesian plane, the xy plane, and now we're going to do it on the real imaginary plane. This is called an Argand diagram now. Argand diagram, when we work on this complex plane now, Argand diagram, not the Cartesian plane or diagram. So we're going to see a lot of the same sort of mathematical relationships, though, aren't we? You could expect that. All right, let's come down and see what else can we do with them, and stay in touch here. Let's go and have a look. Okay, so the first one, and screen clippings here from Hayes and Harris publications, we're going to just start using this Argand diagram here to represent our complex numbers. So what about Z1 is 3? Now Z1 here is a real number, there's no imaginary part. But you can still plot it on the complex plane, because remember, the set of reals are contained within the set of complex numbers. Okay, aren't they? They're just a complex number with no b. B is equal to 0 implies, oh okay, let's put it here, z equals, that implies z is a member of the real number set. Okay, and all complex numbers, or all real numbers, sorry, are contained within the complex number set. Are all the complex numbers where the real part is a number, anything from 0, any real number, but b is 0, so there's no imaginary part. Okay, so here it is down here. We've gone along the real axis 3 units. What about 4 plus 3i? Right, we need to go out 4 here and up 3, there it is, Z2. Z3 is 5i. Okay, let's have a look at that. Here it is up here. 5 units displacement in the imaginary direction only. Neg 4 plus 2i. Here we are out here. We've gone neg 4 and plus 2. You get the idea. Okay, so check those last two out. Pretty simple idea. Come on down and let's get moving with this. Here's another one. Okay. Find algebraically and vectorially. Now we did algebraically earlier presentation. Here it is over here. Adding up 3 plus I and 1 take 4i. Just do it as A plus BI and C plus DI. Remember, collecting the real parts and the imaginary parts. Okay. And then Z1 take Z2. We'll look at it vectorially in a minute. Z1 take Z2, be careful with the brackets because we've got this negative sign out the front. So it's 3 take 1, neg 1 there, and then neg 4i plus 4i. What's that? So it's a total of 5i, and 3 take 1 is 2. So we've done that before, earlier presentation. Let's look over here vectorially at Z1 plus Z2. Here's Z1, so we would displace a point to there, and using vector notions now, adding on the displacement represented by Z2, which is 1 take 4i. So we're going to go 1 and then take 4i from that initial z1 position. So that's z1 plus 2, z2. So we'll think about that. I'll come down and look at this little rule that they've given us here and see if we can unpack that. Z1 takes Z2, as in vector land. Let's have a look. I'll just scrub some of this out here. In vector land now, you displace the point, the origin, to Z1, and then take Z2 means you will go opposite to the direction of Z2, which would be neg1 plus 4i. Look at it up here. It would be neg1 and plus 4i. So the overall resultant displacement, Z1 takes Z2, is to this point here. That's our Z1 takes Z2 vector. And does it check out as 2 plus 5i? Yep, let's tidy the diagram up a bit here. Yep, it's 2 across here and 5i. So it's consistent, as you would hope. We don't want to get two different answers doing it by two different mathematical techniques. Okay, reminder. Draw Z1 first, and at its arrow end draw Z2, and it's a little bit of a monkey see, monkey do rule here, but I guess you know, if you watch all the presentations, and I guess you know in vector land, what you're doing is adding displacements here. Z1 plus 2 is adding displacements on the plane, whether it be the Cartesian plane or the Argand diagram. Okay, so that's why that rule works. Okay, you displace the point or the origin represented by Z1, do that first, and then to the end of that you're going to add the displacement represented by the other vector, Z2. So you're really adding displacements on the plane is a good way of understanding that. Okay, come down and let's have a go and see what you can come up with here. Oops, hang on, I won't show you those for the moment. Let's just come down here and I'll just show you those little ones there. Okay, so here's 2C1. So pause the presentation, have a go slowly through, just be reminding yourself here to do it algebraically, that is just in real and imaginary parts, and then also drawing vector representations for each of those as displacements on the plane. Okay, I'll show you the answers now. We'll come down here to C1, question 1. So check it out. This is very important in this course. I'd like you to work with the Argand diagram. It's usually a key part in the exam. So come down now to question 2, A, B and C. Just check that you're getting this correct. And D. Think of it as displacements on the plane. So here W take 3Z, displace the point W, and then neg 3Z's worth. So the overall displacement will be W take 3Z. I hope you've done a bit of 2D vectors before. Okay, come down and let's have a look at example 16. All right, so here we are, the same sort of thing now. We're going to have 1 plus 2i, 3 take 2i, and find algebraically, so you've got a double Z, so there it is algebraically, plus 3 take I, expand this here and pick out the real parts there and the imaginary parts. Very important to set it up as real plus imaginary part. And if we did it vectorially, 1 plus 2i, well first of all 2z, so if we plotted 1z, 1, 2, and then 2 displacements of that takes us up to here, and then if we add w, which is 3 take I, so it's down there, then the final displacement is there, which would be the sum of the two displacements, or the two vectors 2z plus w. And does it check out? The overall 2z plus w overall displacement is 5 in the real direction and 3 in the imaginary direction. So it's all nice and consistent, bringing in your vector approach here. What about z take 2w? There's z, watch this, a negative sign, take 2w, so when we expand this it's going to be neg 6 plus 2i, then collecting up the real parts, neg 5, the imaginary parts, 4i. Okay, so that's what it should look like. Let's come over here to the diagram. Let's go Z for a start. So starting at an arbitrary point, Z is 1, 2 to there, and then we want neg 2W. So what's neg 1W would be neg 3 plus I, because W is 3 take I. So neg W is neg 3 plus I on the end there. So we're there, and then we've got to do it again. It's 2W, so we're out to there. So Z take 2W is this vector here. The sum of the displacements of this point, Z, and then 2W. Okay, so overall, what have we done in terms of the Argand diagram? We've moved effectively neg 5 in the real direction and plus 4i in the imaginary direction. There it is there. Okay, so they should be consistent. So when you do yours down here now, just the 4 parts there, I want you to check that it is consistent. You don't have to start at the origin. You can start at an arbitrary point like the book has done here. Any point, just get the displacements correct. All right, have a go. Let's come down now, have a look at question 4. And down below, if you want to toggle forward, are the solutions, of course. Okay. Explain with illustration how to find geometrically. Okay, those complex numbers there. And of course, when you've got these, all Z's here, you're just going to let it be A plus BI, if you like. A in the X, or the real direction, and B in the Y, or the imaginary direction. Come down and look at the solutions now. Oh, here we are. There's 3, A, B, and C. We'll finish off with D there. And then 4, just any arbitrary Z. Okay, up here, show Z, show how to get 3Z. Okay, in general. Okay, E, F, G, and H. Just watch some of these here. 2 take Z. 2 in the real direction, and then neg Z, and so the overall displacement is this little dude down here. Conjugate here from before. Important relationship, isn't there, between the conjugate and the original complex number. Right, study those. Might want to talk to your teacher and other students about that. They're interesting. Let's come on down now and have a look. Of course, you knew this was coming up because conjugates, as I said, are important because they are an important pair to any complex number, because their sum and product are real, and therefore they can form a real quadratic equation. Okay, if you like, they can hide in the quadratic equation. You don't see them in the coefficients because their sum and product are both real. So this is a definition of conjugates, isn't it? If Z equals X plus YI, the conjugate is the real part with the opposite sign between that and the imaginary part. So you must always write a complex number as real plus imaginary part times I. Or here, they've got the I in front of the Y. Okay, so what do you know? Well, let's have a look. Let's have a look at this diagram. Well, to start with P1, I guess we should start with P1. So P1 is 2 plus 4i, and its conjugate would be 2 take 4i. Okay, P2, 4 plus 1i, its conjugate would be 4 take 1i. You're seeing a pattern here. Have a look at the pattern. Have a look at where they are on the plane. I'm drawing that line in to give you a hint. Q3, 0.3, here it is. And what would its conjugate be? What do you reckon? Okay, so here it would be 0 neg 3. Okay, because this is 0 plus 3i. This is 0 take 3i. And here, neg 3 take 2i. Neg 3 take 2i, that complex number there, represented by that vector. You can also think of it as being represented by the point, but it's really a displacement of the point down there using a vector idea. And then what would be its conjugate? Neg 3 plus 2i. So that would be up there. So all these connecting lines, can you see what's happening with conjugates? One is the reflection of the other in the real axis, isn't it? Because you're changing this sign here either way, going up or down, and so it's really quite easily identified as a reflection in the real axis, what used to be the x-axis here. So just think about that. You can see why that would be the case. Let's come down and use it now. There it is. If z is OP, its conjugate is OQ, where OQ is a reflection in the real axis. So you might take some notes of these things that we put down here, just as little prompts to remind you later on. All right, let's come down and do some Argand diagram work. Okay, so plotting some conjugates. This is very important in the exams in this course and tests and so on, looking at the relationship of complex numbers on the plane and the geometry around it, because we're going to see quite a few geometric aspects coming up again from, as I said before, coordinate geometry and vector geometry, and you're expected to be able to meld those into complex numbers now. It's an interesting part of the course. Okay, so have a go at those. I think things like this one here, explained by illustration that z take its conjugate is always purely imaginary, or this one here is always real. Okay, have a look at the diagram and see if you can explain that. And when would it be imaginary and when would it be zero, looking at the diagram. Okay, so some interesting points for discussion in class there. I think that one should be discussed. All right, so I'm going to show you the answers now. So come down and let's have a look. That's 1A and B, and the others were discussion, so they've only put in 4 there. The conjugate of z is z. So let's just go back up and have a look. We'll just come here, see if we can get this. So explain with illustration that z plus its conjugate, well, they've done that here. Z plus its conjugate is always real. So can you see that z and its conjugate there are going to be identical in real and imaginary parts? So here, overall, the imaginary parts are going to cancel out and you'll end up with a displacement straight along the real axis. That's our illustration. Z take the conjugate of z. Let's have a look. If we did z there, let's use their diagram, and then we add the conjugate of z, right, conjugate of z, so the real parts are the same, imaginary parts are negative, so when you take it, the real parts, if you like, going to cancel out. That displacement for z is going to be made negative and added on, so you're going to have no displacement in the real direction. It's just going to be double the displacement in the imaginary direction. Okay, can you see that from that diagram? And what that means is you'll always get it as a purely imaginary number. Here it's what, neg 2i in this diagram, if you like. But what distinguishes, can it be zero? How could z take, the conjugate of z be 0? Well, it would have to be that the number was just real, wouldn't it? Okay, because what we're saying, just 0. So it'd be 0 plus 0i, and 0 take 0i. So you end up with double the imaginary part when you subtract them, if you like. Okay, you subtract them. So it would have to be a purely real number so that there was no imaginary part left at the end. Okay, so this would be 0 here if the original number z was real. Okay, the real parts would cancel out and the imaginary part would be 0. All right, so think about that, and you might do it also algebraically. All right, let's go on and have a look. Yes, there weren't any answers for that. So what's next? Well, you can see what we're doing. We're reinventing the wheel to a certain extent. We're going to do the sorts of things with these vectors on an Argand diagram that we've done with vectors elsewhere. This time they represent complex numbers, and also with coordinate geometry. So what might we want to do? Well, we might want to look at things like lengths of lines, or distance between points, or distances between complex numbers on a plane. Okay, so let's have a look at that. It's pretty predictable now that we're on an Argand diagram what we're going to have to do. So here we are, we're going to define this. If we plot a complex number starting at the origin, we want to find its length, if you like, the length of that vector. And you know that from our previous work with two-dimensional vectors, the vector 3, 2 means displacement 3 in the real axis and 2 in the imaginary direction. And therefore its length by Pythagoras, right, its length by Pythagoras will be the square root of 3 squared plus 2 squared. Now we call this the modulus, oh there's a new one, the modulus or absolute value idea. Well, we've used that before in other courses. The absolute value, called abs if you like, on any technology or calculators, is the size of the number. So you can have the absolute value of, or the modulus of, a real number here. Absolute value of -3 is how far -3 is displaced from 0 on the number line, and that's just 3 units. So how far is 3 displaced? That's also 3. Okay, so that's the absolute value or modulus of real number sets. So what does it mean here? It means, again, the size of it. It's usually called the modulus with complex numbers, not abs, absolute value. Same idea though. So we want the size of this Z, the length of that vector displacing, if you like, the origin to 3, 2. So it's just going to be by Pythagoras, isn't it? Square root of a squared plus b squared. So here it's going to be the square root of 3 squared plus 2 squared in that right angled triangle there. All right, so you get the idea. We're starting to build it all into vectors now because we're on an Argand diagram. All right, so how do you do it on the calculator? This is the first use we're going to see in these presentations of the calculator. But we go to run mode. This is Casio 9860 Plus. HI, HB and TI have similar functions. So if you choose that and also push option here, option in there, F2, just below F2, sorry, hit option, you get this window, and I think you can see something there, CPLX, that's complex, and you choose that by hitting F3 in there. Okay, so if you do that, you get this window. So these are the options that you can work with on the Casio with complex numbers. Okay, so what do we want to choose? Well, we want to choose, let's not put that one there, we want to choose abs for absolute value, which we call modulus in complex number land, but on the calculator they call it abs. You could do it for a real number as well. And here we've got argument, haven't done that yet, that's coming up in the next presentation. We have done conjugate, so if you hit that it'll produce the conjugate of the complex number. Okay, so you've got those options. What we want to do now is look at the absolute value or modulus. So it's in there at F2. So if you hit F2, we get this little symbol there with the modulus signs around a place where you can enter the complex number. Okay, so you might notice here the I. So what you would do is hit 3 plus 2i and come down to this window over here. Don't worry about that little sign in there. That's the flashing cursor because I couldn't get rid of it. If I hit execute, I'd come to this window and I didn't want that yet. So 3 plus 2i can be entered. Just remember this is your I here that you'll use in that window. So you get that, and the absolute value of that is root 13, 2 squared plus 3 squared. So that's the way you could do that on the calculator. Mostly you can do it very easily by just using Pythagoras, can't you? But I just bring that in so that you're aware of that. Okay, let's go on and see if we can do some. So here's example 17. finding the absolute value of this. So what are you going to do? It's the square root of the real part squared plus imaginary part squared. Always, of course, isn't it? Because let's just draw it differently from that. So if you have a real displacement, imaginary up there, the length of that is going to be real part squared plus imaginary part squared by Pythagoras. Okay, because we're still on that Cartesian plane where the displacements are at right angles to each other, the axes are at right angles to each other, so Pythagoras to the rescue. All right, 3 take 2i, same thing, 3 squared, and then neg 2 in brackets all squared. Let's just have a look at that. So here we've gone 3 and then neg 2 here. But that doesn't affect the length of this, it's this squared, and the size of that is neg 2 squared is 4. So you're going to have the same idea here. And neg 3 take 2i, don't forget to square the neg 3 and the neg 2. Use a bracket, do not ever enter into your calculator that, because that means square 3, it's just, the square's just sitting over 3, and then make it negative. So that would not be correct, that's wrong. We want neg 3 all squared, so it's a positive. You've got to actually tell the calculator that, otherwise it will just square the number over which the 2 is sitting. Okay, so here we have our rule by Pythagoras. The modulus or size of the vector representing complex numbers z is square root of real part of z squared plus imaginary part of z squared. And of course that's a length, it's a real number, and that's pretty obvious. All right, come down now and let's have a look at 2c3. So that's just looking for the size or modulus of the complex number, the length of that complex number, the length of the vector representing a complex number, if you like. Okay, so a lot of things to do here. I want you to do all of these very slowly and carefully, because you're going to, in an inductive way, investigate some rules for modulus, like we had rules for the conjugate back in the earlier presentation. Okay, so and then do this one with a plus bi, and try to see if there's a pattern in what's happening with the modulus or length of a complex number, length of the vector representing a complex number. All right, I'll show you the answers now. So here they are, question 1 through 3. They haven't got the last one there, showing that it's those relationships are true by using z equals a general number a plus bi, a general complex number a plus bi. All right, so look, we're going to do some things with these later on. You might be able to prove them with a plus bi even, and then perhaps using the process of mathematical induction, try to generalize them. Can you expand this to a product of n complex numbers, and would the modulus or size be the product of the individual moduli? Okay, all right, we might have a look at that later on. Let's go down now and continue building up our skills. So it's important to have lots of practice. Don't just look at maths, you've got to study it, to understand it, go up the hierarchy to really seeing what's going on, and then do lots of practice. Okay, prove that the modulus of a product is the product of the two moduli. Okay, so let's use a plus bi and c plus 2i. Okay, so z1, z2 is that, just be careful with our expansion, real plus imaginary part. Once you've got that, you can find the length because it's the square root of real part squared plus imaginary part squared. And there's a lot of expansion to do there. I hope you're good at that. Remember the old rule, a plus b squared, first one squared, plus twice the product, plus the second one squared, that idea. If there's a negative, of course, in there, that product will go negative. So that's a quick way of going from here to here. You should be good enough to do that. First one squared, twice the product, which is negative here, plus the second one squared, and do it again for the one with the plus inside. And so when you do that, of course, we've got a real number, because we're just squaring the real part and the imaginary part. And if you factorise that, you see that c squared plus d squared is a factor of both the a squared and the b squared term, I suppose. These cancel out, and package them up. A squared c squared plus a squared d squared, b squared d squared plus b squared c squared. So we can factor that c squared plus d squared out, and then of course you've got the square root of c squared plus d squared by c square root of a squared plus b squared there, which are the two individual moduli multiplied together. So it's just a matter of juggling terms. So we've proven the first case. I wonder if you can do it in n-land, go from z1 up to any number of z's where n is real, zn. Would you be able to break it down? We'll come and look at that. All right, so let's go down and have a look at some little problems here. And these are important ones. I think there are only the 5 through 10 here. So here we are. This is the inductive argument here, isn't it? And we'd like to prove this later on by the process of mathematical induction. So remember what you've got to do. You've got to show the same inductive step, the continuation of the pattern. Okay. So that's the process that we talked about right at the end of the last presentation. So you might go back and make sure you've noted that process down. And here we are. What is the generalisation? Well, I'd like you to try to write the actual proof for that. We're starting with case n equals 2, which we've proven above, and then using the inductive step and generalising so it'll be for all n greater than or equal to 2. Okay, here's another one here, using a plus bi, c plus di if you like, and proving that result. And then the rules, simplifying some of these that were the rules that we found back in the earlier exercises. Okay, I think this is okay, using just the idea of real and imaginary part and some relationships between cos and sine. A result of 6, okay, so that's interesting. Z to the 20th. Okay, what could you say? Think about that. Okay, let's go on and have a look at 11. Yep, well, that's going to be a bit messy algebraically. Have a look and see what you think. Let's have a look at the answers now. Okay, there's some answers. And of course, I'd like you to have put in an inductive proof for that product. Okay. Now, what should we do here? Maybe we'll leave that to later, showing that inductive proof, and see how you go, or should we do it now? Okay. I don't think I've got room here just to have a look now. So I'll do it at the end. I'll come back and look at that proof at the end. Okay. So let's look at what we've got so far. Summary of modulus discoveries. Okay, so a couple of things there that we're summarising that we've found. Okay, let's have a look at the conjugates from before. So building up quite a few different properties here. So you might copy these down and just pretty common sense. It's what you'd like to be true. The modulus of a product is the product of the moduli. Come down now and we'll have a look at distance in the number plane. And right at the end, I'll go back and do that inductive proof for the product of the modulus of two complex numbers. Okay, distance in the number plane. Okay, well, let's have a look at this. You would have guessed that we want to find the distance between points on the Argand diagram as we have in coordinate geometry. So let's have a look at complex number x2 plus y2i and x1 plus y1i. Let's do it algebraically. What is the modulus of z1 take z2? What's the modulus of x1 plus y1i take x2 plus y2i? Which is collecting up the real part and the imaginary part. Modulus is the square root of the real part squared plus imaginary part squared. Hey, but hang on. I recognise that. That's the distance between these 2 points. Well, that's interesting. So what we've done here, algebraically, we've proven that the size of the difference of two complex numbers is the distance between them. Distance between P1 and P2. Oh, P1 and P2. Now that's interesting. The distance between P1 and P2 is down here, the same using coordinate geometry idea. I hope you've spotted that from coordinate geometry. That would be that length, wouldn't it? And it's equal to the size of Z1 take Z2. Ooh, so what's the connection between this line and Z1 take Z2? Let's have a look at that, because the length of that line is the same as the distance between the 2 points, which means it should be Z1 take Z2. Let's go down and have a look. Here we are. Is it Z1 take Z2? If we go Z1 and Z2, if we come by sum of vectors around a closed figure, we can show this very important result. Okay, so we go Z1, and then if we go here, it'll be neg Z1 plus Z2, opposite to that vector, and then plus Z2, we're back to 0. Wow, that's true. Let's just do that again. Z1, take that vector Z1, take Z2 across the top, and then take Z2 equals Z1 take Z1 plus Z2 take Z2 equals the 0. We're back to the start, the 0 vector, if you like. Wow, so that we've just looked at a way of realising that that vector there is Z1 take Z2. That's why its length implies its length was the distance between the 2 points. Okay, that length was the same as the distance. So here it is here. If you like, looking at it as the book's done it here. But I like to think of it as emanating from the idea that sum of vectors around a closed figure, which means if they all add up to 0, this must be Z1 take Z2 going that way, would give you a sum around the closed figure of that. And they've done P2, P1 is those two, and then rearranged it. That's another way of looking at it. And so this is a very important result. So come down, I've written something about this. This can be an important way of thinking about Z2 take Z1, rather than just, now what Z2 take Z1? Well, usually Z2, and then if Z1 is going this way, we would add on the negative. So that's true as well. Okay, so this would be Z2 take Z1, done in the conventional way, adding on the negative of the vector representing the complex number Z1. Okay, so that's one way, but this is a handy way where you think of it around a closed figure. So Z2 take Z1 would be done differently. Let's go back up here and have a look at this one. So here we've got Z2 take Z1 as being the final side joining Z1 and Z2. So what we could do, what would Z2 take Z1 look like if we did it the other way? Go Z2 and then add the negative, there's Z1, add the negative of Z1. Can you see we get the same vector? That plus that takes us to there. So Z2 take Z1 would be our final side. Okay, so it's the same, going to be the same as this. Okay, Z2 plus a negative of Z1 down to there. Okay, so we're going to get the same vector. Oh, I've done it the other way, haven't I? I should have done Z1 take Z2 because it's in the wrong direction. Let's just do that again. I've done Z2 take Z1, so that would be that way. Let's do it the other way. Z1 to there, and then take Z2 is going to be out there. So the final displacement is Z1 take Z2. Okay, I have the, coming the other way, we'd have the direction opposite. So that should be parallel, that should be parallel there. So can you see it? That's one way of doing it, but what I'm saying to you is one of the handiest ways is to recognise that if you have Z1, Z2 in a closed triangle like that, Z1 take Z2 is a vector connecting from the direction of the end of Z2 back to Z1, because it's sum of vectors around a closed figure. And that does become a very important way of thinking about Z2's take Z1, not just this way, where you to the end of Z2 add neg Z1. That they will be parallel vectors, but it is handy to think of Z2 take Z1 as the vector forms a closed triangle between Z2 and Z1. More of that later on. Okay, let's come down now and have a look at a couple of little things here. Consider the following. Notice that OR represents W plus Z. Can you see that? W plus Z. Here it is. If we put W over here, OR is W plus Z. Okay, or Z plus W. So you can use a parallelogram or a triangle rule here, because it would be parallel to that W there, and you can add it around the parallelogram or the triangle. Now, OM is therefore W plus Z on 2. Now that's interesting, because the diagonals of a parallelogram bisect each other. So if you draw the parallelogram, so it's parallelogram because W's there and you put W there, and if you copy that with Z, if you come out to OM there, OM will be a half the sum, okay, because the diagonals bisect each other. So there's a couple of little geometry tricks that we can pick up from vector geometry and coordinate geometry and properties of, or Euclid's theorems here, that the diagonals bisect each other. So that's an interesting little result there. All right, let's go and use some of these things now. So here we are. Got 2 points on the Cartesian plane. Use complex numbers to find distance PQ and the midpoint of PQ. Okay, so 2, 3 are 2 points, 6, 1. So the vector representing the complex number 2 plus 3i is Z. Representing the complex number 6 plus i is W. Okay, so what's the distance? PQ. So PQ, distance PQ is there. So we can use basically just the coordinate geometry idea by getting Z take W. Okay, because this would be Z take W in that direction, wouldn't it? Z take W in that direction. And so it's the length of that, so let's find Z take W. Z take W. So Z take, or I would have preferred they put take in brackets 6 plus I to explain that that's got to go negative there. So now we have the real part 2 take 6, neg 4, imaginary part 3, and here take 1 or 2i. Okay, so the size of it is that part squared plus that part squared, which is root 20, or here 2 root 5 if you like. Because the root of 20, just remembering that, is the root of 4 by 5, which is 2 root 5. Okay, and then Z plus W on 2. Now, what is that? So here, Z plus W on 2. If we did that, Z plus W divided by 2 is 4 plus 2i. And the midpoint of PQ, therefore, is 4, 2. Z plus W on 2. Okay, because Z plus W on 2 would be, what is it, 4 plus 2i, coming out here, let's plot it, out there, that's 4 plus 2i. So if we look at the diagram, you can see that's going to be our middle point, and it's going to be 4, 2. Z plus W on 2, because it's going to form a parallelogram, if you like, if you kept this going. So that's an interesting little result. Think about that geometry, because that's quite popular on the Argand diagram, doing a bit of other geometry that we've learnt from elsewhere and bring it into complex numbers. All right, let's come down and talk about more geometry on the Argand diagram, and what transformations what transformation moves Z to IZ. Let's look at what happens when you multiply a complex number, any general complex number, by I. So you get IX, or X times I, plus I squared Y. Always put it, very important here, into real and imaginary part. So the real part, I squared Y, that's neg Y, so that's the real part, plus XI. So the size of this complex number is the square root of that all squared plus that all squared, which is X squared plus Y squared. So that's the same as, sorry, that's the size of IZ, and the size of Z is the same. Okay, going back up here to do it on that one. And so they are, let's look at the diagram now. That's the original complex number, X plus YI. And now they are the same length. These are the same length. We've just shown that. And what else can you say? Well, this is XY, and now this is neg YX over here. Okay, so they are at 90. Now, we did a bit of this with our definition of circular functions, where you're doing rotations and talking about the cosine and the sine then. So there's an overlap with that, isn't there? The idea that if you rotate a point anti-clockwise about the origin there by 90, you interchange the X and Y coordinates. We've used that in circular functions. And here it is again, that this time what we've done is multiplied by I over here to get that expression, and therefore we've got the interchange here of the Y making it negative with the X. Okay, and that represents a rotation. So let's just do that up here. If you're on a plane and AB goes to neg BA, whether it be circular functions on the Cartesian plane and all that stuff or not, this represents a rotation in the anti-clockwise direction of 90 degrees, or pi on 2. Okay, so the maths is still the same, isn't it? It wouldn't change, but we are applying it now to a real and imaginary set of axes, an Argand diagram. So the lengths are the same, and the coordinates have interchanged, and the first one now becomes negative. So it satisfies the idea of an anti-clockwise rotation of pi on 2 about O, as it does back in circular functions work. All right, so that's an important trick. Can you see what we're doing? This can be quite challenging because we're asking you to remember all the geometry from other areas which could also hold or be true on this plane. Okay, let's have a look at doing some stuff. All right, so use complex numbers to find distance AB, midpoint of AB for those pairs of points. So I want you to plot those on an Argand diagram and have a good look. So we won't call them 3, 6 and neg 1, 2. We're going to call it 3. Think of it as 3 plus 6i using complex number sort of theory, and neg 1 plus 2i, and then find the midpoint of AB using the idea of the sum of the complex numbers divided by 2. Okay, so because the diagonals of a parallelogram bisect each other. We're going to form a parallelogram by trying to add these vectors up. Okay, if we look at our parallelogram now, can you actually do some stuff with that in terms of Z and W by looking at those two displacements, using a bit of vector theory there. Now down here we've got a couple of interesting questions about triangle OPQ, this one here, and OPR, this one over here. Okay, so you might have a look at that. I don't know whether you know the theorem necessary to do those two. And the theorem that is necessary is called the Triangle Inequality. If you like to think about that, I'd better put this in here. Or if you know it, I'll try and do it without me teaching it now. But otherwise, so pause the presentation, have a go. But otherwise, I'll just talk about the triangle inequality. You might appreciate the fact that if I had a line, I don't know, A, B, and C, and I cut the line here at B and lifted it up a bit to make a triangle, this is one way, simple way of thinking about this, then can you see that if B went to there, now AB plus BC would be greater than AC, to stretch it up and lift it from this point here. If B was collinear with A and C, we would have equality. AB plus BC would equal AC. Okay, if that was in one straight line. But if I cut the line there and lifted it up to form a triangle, AB plus BC would now have to be greater than AC to get the extra lift, if you like. One little way of thinking about it. Not a proof, however. Okay, so the idea of a triangle inequality is that the sum of any two sides is greater than the third, whichever two you choose, because you can think of it being constructed either way. So you might use that in both of those cases, actually. All right, so pause it and have a go at all three, and I'll show you the answers down below. Okay, so here are the answers. Hang on, I'll just move that up a little bit. Just want to focus on that. So there are the answers now. And I'll go back and do part B and C here because they're missing. I think we should talk about those. They are important because they do involve the triangle inequality. Okay, so check that out. Now, down here, I've got something very important. I'm going to show you how to use this in a minute. The triangle inequality is very important in this course. If you use it, you must show the connection to an appropriate triangle. So remember what the triangle inequality is. Okay, so let's have our sides here. Let's say PQR. Okay, the sum of any two, let's say PR plus PQ, must be greater than or equal to QR. And they're only equal if they are collinear, if the 3 points are collinear, that the sum equals the overall distance. So it's any two, the sum of any two sides. I've done PR plus PQ must be bigger than QR, or QR plus PR must be bigger than PQ. Okay, from the same reason I just used before, just to understand a little bit about triangle inequality. Let's go back up then and have a look at this one. Okay, so we'll scrub this out and have a look at these two problems with that diagram. Let's look at the first one and how you set out the proof. OPQ, that's this triangle in here. Explain why Z plus W is less than or equal to Z, size Z plus size W. So this is W here. Okay, so you can see the displacement Z plus W, this is the side Z plus W, represented by that vector. So you'd have to put that down. OQ is equal to Z plus W. Now, so this is in triangle OPQ. Then you could say, now you've shown the connection. I told you you have to show what you're going to do or use fits in a triangle. And then you can say, by the triangle inequality, any two sides, sum of any two sides. So what do we got? We'll use these two. The length of Z plus the length of W is greater than or equal to length of Z plus W. Okay, and equality only occurs when the points are collinear, OPQ collinear. Equality if OPQ collinear. Or Z and W are in the same direction. All right, so that's that one. What about this one here? This looks a little bit different. Okay, well, let's look at that one. So this is up in triangle OPR. That's this one here. Okay, again, we should do the same sort of thing. Now, I'll scrub this out. I haven't got room here. Come back and look at that by toggling back. So in triangle OPR, what can you say? Well, you've got sides W and Z. What did we say this would be? This would be W take Z, right? If we go that way, W take Z. So the sum of vectors around a closed figure. Okay, that would be W take Z. Now use this one, that's important. Oh, well, hang on, let's look down here. We want Z take W. So let's put it in the opposite direction. This would be Z take W, okay, down there. Okay, so we're using that only because I spotted down here, that's what they want us to talk about. All right, so what could we say? Well, we don't know a difference for a triangle inequality, but we could add that over the other side, couldn't we? So let's do it. In triangle OPR, RP, that vector, is Z take W. By the triangle inequality, we should write that. Now we've shown the connection, we've shown they're all in a triangle, so the length of Z take W plus the length of Z, I'll use those two, I'll add up that one and that one, must be greater than or equal to the length of W. Okay, we don't need that, there's complex number. Okay, so now we can say, just transposing terms, it's W take Z. Okay, and equality when W and Z in the same direction or collinear. Then they would all be, then that equality would hold. So that's a little tricky do here, just let's clean this up a bit, that I'm thinking of that as that, and therefore we can rearrange it at the end and have a length of W take length of Z. But the idea here is very important, that you have to name the triangle, show that what you're working with, and the W and Z don't matter, they're already in there, but show that what you're working with would be the other side of the triangle, and then you can invoke the triangle inequality. So just come down and make this note for later reference. And this is very important. The triangle inequality is to be used in this course, but you must show the connection to a given triangle. All right, well, I guess you're getting a little bit tired now, but I do want to put that, I've decided I will put that proof down the bottom here of the modulus of the two complex numbers. Okay, so here, let's just go a little bit further and do here. So what we're going to do is try to prove that the modulus of Z1 up to Zn equals the modulus of Z1, modulus of Z2, modulus of Z3 up to the modulus of Zn for all n greater than or equal to 2. Okay, so it's a generalisation, remember. From the earlier presentation, we're going to use the process of mathematical induction. So here's the proof. Now I'm not going to put it in full. Case n equals 2 is modulus of Z1, Z2 is modulus of Z1 by the modulus of Z2. Now we've got to do this, but I'm not going to do it here. I'm going to say proven from the earlier question 1 or whatever it was. But we must prove this using A plus BI and C plus DI, but we did that up in an earlier example. So now we go case n equals 3. Case n equals 3, and that is, let's look at it, modulus of Z1, Z2, Z3 equals. Now, we've got to use the same inductive argument. That's one complex number times another. So that is modulus of Z1, Z2 by modulus of Z3 from case n equals 2. We're showing that if it works for 2 up here, and you can split them, we'll think of this 3-term one as a product of 2, and then we will split it again, modulus of Z1 by modulus of Z2 by modulus of Z3, and that's from case n equals 2 as well. Okay, n equals 2. Let's do case n equals 3. N equals 4, sorry. So this is Z1, Z2, Z3, Z4, and we're going to use the same process. It must be an identical repetitive step, otherwise you can't invoke the mathematical induction idea. So this is thinking about 4 as a 2, so it's the modulus of this first one by the modulus of the second. We can break 2 down, by case, from case n equals 2. Let's tidy that up a little bit there. Okay, and now we can break this down because that was part of our whole process. We're building, aren't we? We're building, and this was from case n equals 3 above there. Okay, so here, really should go back and put true for case n equals 3. Therefore, true for case n equals 4. Put that. Let's go down a bit here and keep going. We should do another inductive step. Case n equals 5. Here, Z1, Z2 up to Z5 equals again, breaking it into 2. Z1 up to Z4 times Z5, and then splitting that in the same way, exactly the same way as we did in previous steps, and labelling that from case n equals 2. The 2-step idea, common again, you've got to show the pattern, and then you can do, you're picking up the previous one. Must be identical pattern in each of these. This is from the previous one, case n equals 4. Therefore, true for case n equals 5. Okay, can you see the important thing is from the very outset, going from case n equals 2, let's go back up, from case n equals 2, here, there, the way in which we go to here, and then to here, and then to here, what the initial inductive step followed by 2 more, we're establishing a pattern. This is the inductive step, and it must be the same, the way you go from one to the other, okay? The idea that you break it into 2, and that you use the previous case, yes, break it into 2, and use the previous case to get to there. And same in this one. So you break it into 2, use the 2 case, and then to get from here to there, you use the previous case. That must be the identical pattern here. So here, continuing the inductive process, because you've recognised a pattern. continuing the inductive process using the pattern, if you like. Don't have to put that, but I want you to see that it must be the same pattern. You would go here, Z1, Z2, up to Zn is Z1, Z2, up to the one before, times Zn, showing the 2, which is therefore this one, Zn take 1 by Zn. Okay, again from the initial case, case n equals 2, splitting into 2. And then this one up to Zn take 1 from the case, previous case, case n equals n take 1. Therefore, the proposition is true for all n greater than or equal to 2 by the process of mathematical induction. So that all of that should be stated. Okay, so that's how you do that one. Now I'm sorry it's taking a bit longer because I've gone into that, but this is a very important idea, this process of mathematical induction, and as I said before, it can be asked in various spots in the course, not just in complex numbers. So there will be a further presentation on that later on, and also comparing it with the principle of mathematical induction, which is a bit more algebraic. All right, look, thanks for hanging on there. I hope you enjoyed all of that, and I hope you're building up some skills. There are a few more presentations yet. Complex numbers are really going to explode. So I'll catch you then. Cheers for now.